All right, physics. We left off. We finished a lab. We had talked about static electricity. Talked about these different situations of things that are charged and how they interact with each other. I'm going to kind of finish up here talking about how charged objects continuously kind of influence the environment around them through this concept of what we call the electric field. That was a terrible straight line. Yeah, sure, good enough. But through this concept of the electric field, all right? Now, the premise of the electric field is that everything that has a charge exhibits an electric field, right? And this works in much the same way that any object with mass has a gravitational field, right? So the Earth has this enormous mass, and as such, it has this big gravitational field around it. If we want to escape its gravitational field, we have to be going very fast, or we have to be kind of, in order to get far away from it. That's how we landed Perseverance on Mars. We got a rocket ship, goes real fast, gets away from the gravitational field. Electric fields work kind of the same way. We have this nice visual that we like to use for an electric field. So let's say that I have, I can use. My favorite is when my technology only kind of works. Hey, there we go. Let's go with blue. So let's say that I have this positively charged object. I'm actually going to move it down a smidge because I will want a little bit more room. And I want the field lines around my positively charged object. I'll draw them still in blue. Well, let's do it this way. Field lines will always extend perpendicular to the surface of the object. All right, so the electric field is the shape of the electric field and the relative strength of the electric field is going to depend heavily on the actual surface of your object. All right, now this round object has these lines come out, and if you look, you should see that the lines are kind of closer together, close to the object, and they're further apart. They spread out as you get further away from the object. How close the lines are, like the line density, for lack of a better term, but how close or far apart the lines that you've drawn to show the magnetic electric field for an object represent how strong that field is. If they're close together, it's fairly strong. The further apart they get, the weaker the field gets. If I were to draw, if I had a positively charged, like, flat surface like this, then my field lines would extend perpendicular to the surface, and they would kind of just do something like that. All right. Now, the other thing about electric field, so the visual helps us kind of look at a field and say, okay, well, because the lines are close together here and further apart here, I know that this is stronger close to the surface and weaker further away. These lines are all the same distance apart, so they're all going to stay the same strength. The other thing that we need to keep in mind is that it needs a direction. Electric fields can push or pull things away, depending on how they're charged. The way that we orient an electric field, the way that we determine the direction of which way the electric field points, is by asking, what would a positive charge do here? What would happen to the positive charge if I put it in a spot, right? So, generally speaking, the electric field will point away from a positively charged object. And let's say that I have another plate down here that's negatively charged. It would point towards a negatively charged object. Electric field diagrams are straightforward enough. If I were to look at this, and I had point A and point B, and I asked where is the electric field stronger, at point A or at point B? For the example on the left, point A has a stronger electric field because the lines are closer together. If I were to look at the example on the right, and I had point A and I had point B, they actually feel the same amount of electric field because the line spacing is the same. It's actually the same for point C because the line spacing is the same. The electric force that they feel is dependent on the electric field. It's also the same because the electric field is the same everywhere, so the electric force is the same everywhere. Now, electric field has a visual piece. There's also a math piece, right? The math piece that's involved, again, my technology. One day, all of my technology will work perfectly the first time. Today is not that day, and I'm okay with that. There it is. All right, there's a mathematical component to it. On your reference table, we have already talked about the electric force formula, which is K. Oh, you guys don't. That doesn't mean anything to you. K times Q1 times Q2 over R squared, right? And we know what kind of like all of these things mean. K is the electrostatic constant. Q is charge measured in coulombs. R is the distance between charges measured in meters, right? The electric field is represented by a capital E. And field. And it equals the electric force divided by Q, which is the charge. Right? Now, I have one thing to point out about charge, right? Because I'm going to have you do some practice questions, and there's going to be a couple sets of practice questions. One set just to do the visual stuff, one set to do with the mathematical stuff, and then we'll wrap all this up and we'll start talking about current electricity soon. But what I need to pull up is nope, that's wrong. Please stop. I was so close. I misclicked by that much. Nope, missed it again. One take, kids. One take. Physics reference table. Goodness gracious. Alright, I need the electricity page. Let's insert that. Oh gosh. Guys, you can't make this up. Where? Oh, is that it down there? Look, wow, that's really organized. That's amazing. Oh, because it put the... One of these days, all of my technology is going to work perfectly. Oh shoot, I actually need more than one page. So let's undo that entirely. Joke's on me. Try again. Physics reference table. I actually need this page and this page. Let's insert them both. Alright. So, why? Why are we... Okay. I resized it and now I can move it. Cool. And now I can't move it again? What? I'm clearly going to have to turn it off and turn it back on again. Oh, now we rotated it. This is outrageous. Unbelievable. Impossible. Wait, was that the right thing? Oh, that was the right thing. Goodness gracious. Reference table. Sure. You know what? Just give me one page. If I can have and move one page, I would rather have this page. So, can I move it? Can I move it, please? I just want it over there. Oh, okay. Now I want it up. I'm being picky. I shouldn't be picky, because it actually worked that time. What do all these buttons do? Ink grab, like, lock to... Oh, don't lock to background. No, don't. time to check on other things that my computer is doing. What other things are you doing that you are freaking out for? Can you freak out less, please? Yep, I can draw on you. What if I resize you again? Will that let me move you again? No? Well... know what? That's good enough. It's next to it. Okay. I want to point something about the charge. And if you want to, if you have like a physical copy of your reference table that you like to use, you can make this note as well. The note that I think you should make, that I would make, has to do with this information here, right? The elementary charge, which is 1.6 times 10 to the negative 19th coulombs. It's represented by lowercase e. This is the charge of the proton or the electron, depending on if you need it to be positive or negative. All right. The exact charge of the proton, the exact charge of the electron is 1.6 times 10 to the negative 19th coulombs. All right. Last year we just said proton was +1, electron was -1. Technically that's true, because last year when we talked about it in terms of E. So the charge of one electron is -1e. It's negative this much charge. The charge of one proton is +1e. It's positive this much charge. Now we'll do some conversions with this. You see that elementary charges, and you see electron volts down here. We'll talk about that in the very near future. However, for right now, there should be at least one assignment up. A second assignment will probably go up. You're going to see one that is basically just the picture representation of electric field, so dealing with the arrows and the relative strength of how that looks, or perhaps drawing the arrows yourself. The second one that you will see will be on the math, so on actually using the equation and recognizing if you have to do something with electric field and you think you only see force and you don't see anything about charge, look and see if the question told you that you have an electron or you have a proton. Because if they told you you have an electron, or they told you you have a proton, then you do know the charge. It's the elementary charge, right? That's why, I wanted you to kind of grab your reference table, and I wasted a lot of time there trying to get the stinking page in there. But, right, this is kind of a end of the road for this part of electricity. The next piece of electricity that we will be looking at is current electricity, so things actually moving around. Batteries, plugging things in, how all that stuff works. But that is a video for another day. Until then, kids, take care of yourselves. Make sure to keep checking my CBA, look for those assignments, turn those in, and I will... before I sign off here, I said to check my CBA. Please, really check my CBA, make sure everything is in. There are a couple of people, maybe a handful of people, that didn't take the quiz from before break. I need y'all to take that quiz, all right? So I've opened it. It's like open. You should be able to access it. If you have trouble, email me. This may be the only time that I reach out to you to make sure that you do that. So if you find a 0 later, I'll address it again later. But please continue to check my CBA. Make sure that you turn things in. If you find something missing but you turn it in later, send me an email to kind of remind me to check, because otherwise I won't go back and check, alright? Okay, that's actually it. Until next time, whenever that is, take care, y'all.